going to look at Chapter 6, Section 6, Frames and Machines. Okay, the ideas here, frames are used to support external loads. Okay, so just starting with that. And you can think about how it's different and how a frame is different than a truss. Okay, so as we go through, this is one of the questions to think about. All right. And what do we need to do? Of course, similar thing to a truss, we need to design a frame that can, so to make sure that it can support whatever load, right? And we're going to look at the forces of the joints and supports. Okay, machines, right? So machines actually apply a force, all right? So we're going to look at, and this is the same thing, it's like think about what's actually happening here and how this is different from trusses and frames, right? How machines differ from there and how the analysis will differ as we go through, okay? Okay, and the same thing, we're looking at loads of joints and supports. So same tools, right? The same ideas we have. We're going to look at forces and moments, all right? And we care about, yeah, can the frame and can the machine support the loads that are going to be applied? That's really the end result here for our design, our end goal. Okay, a couple of examples here of a frame and a machine, and just some general terminology for you. Frames are generally stationary, okay, and machines contain moving parts, right? Okay, so steps for analyzing a frame or machine. Same thing, draw a free body diagram. Identify any two force members, right? So this is very helpful for us in terms of breaking down the problem and simplifying it, right? We can have two force members. Like, as we can see, this one here, the only forces acting is FAB in both directions, okay? Also, forces acting on a contact surface, okay? Pin and a member are equal and opposite, which is our expectation, because any time you analyze any point here is that whatever force is acting, react, like here as an example, whatever forces are reacting, these reactive forces here, there's a force being applied on this that's equal and opposite, right? So my reaction might be pushing up, this thing's pushing down with equal and opposite force. If I have a reaction off to the left here, this bar is applying a force equal and opposite to this off to the right, okay? Okay. So, and if you have a joint that's with more than two members or an external force, it's good to have like a separate free body diagram of that. Okay. And here's an example. Here's an example of it over on the left. Okay, as a strategy, all right, this is, it's similar to what we've done in the past with like trusses. Develop a strategy, apply the equations of equilibrium, right? So it's the same thing. We're solving for a frame or a machine. We're looking for applying these equilibrium equations, right? If it's 3D, we have, 6 possible equations. If it's 2D, we have 3 possible equations we could use, okay? And just by applying this strategy, it can simplify your work. If you find equations where you have form a single equation and single unknown, then you could solve for that and maybe substitute back, or move forward and substitute into other equations so you can solve for the other unknowns. So the first ones you set up should be equations where you only have one unknown, right? That makes it easier typically in the solution. Okay, so a lot of the problems are going to be challenging, take a little bit of work. Of course, we'll stay with the simpler problems at this point, and a lot of practice is needed, of course. That's with all engineering, okay? Okay, so here's an example of a frame. And how you could see, is this like a truss structure or not? It's like some of these connection points, these look like, supports that we would see in a truss, except this is not like a long, thin member that's connecting between 2 points, right, or a long straight member, we now have this like angle bar, so we can see how that varies from what we would see in a truss problem. Okay, so draw a free body diagram of a frame. In this case, the frame member BC. The question asks, why pick this free body diagram of this frame member? Well, what are we looking for? We're looking for reactions at C and magnitude of reaction at B. So we're looking for something that's happening essentially over in this part, right? Okay, so that's what we were concerned with. And then apply the equations of equilibrium and solve for the unknowns. Okay. Okay, so the first part of the problem, draw the free body diagram of this member. And we have to make sure, we have all of the forces and moments, reactions, everything associated with it, any reactive moments, with our diagram, right? If we're missing anything, of course, our solution will not be correct. Okay. So we're looking at from B to B and C, so we just do it for this member for this portion of the frame from B to C, this L bar, I'm going to call it. So we draw the free body diagram. Here is our moment couple. Here is force and where it's acting. Here are reactions. That this is a pin support, so we don't have a reactive moment. We only have reactive forces. And the author chose to draw it in these directions. And then we have another one, a reaction here at B, okay, straight along this bar. Okay, so one of the things we note is that this is a two-force member, okay? So we can leave it out anyways, because we don't really, we could make a free body diagram here, but this really doesn't do anything for us in terms of helping to solve the reactions at these points, right? So these are what we're looking for, B, Cx, and Cy, okay? So we have some equations that we can use for equilibrium, and just following the general approach to come up with an equation that has only one unknown, if we can find that. And what we could do, you notice that if we do something here, if we do the moment about this point at point C, this is out of the equation, this is out of the equation, and we only have B as our unknown, okay? Now, you have to think about this one in terms of, this is not, straight along the horizon or, vertical. So this is going to have two components, right? We're going to have an X and a Y component associated with it, okay? And in this case, the author actually drew this as being, as we have defined it, positive in the counterclockwise direction about C, okay? So this is negative, and it's 3 over square root of 10, right? Because this is this length, this is square root of 10, this is the length of this line, so using the law of similar triangles. And so we're doing this component right here, right? So this component of the force, and it's acting 1 meter down from the line of action of this point, okay? Or 1 meter down from a line of action here that's perpendicular to it. Okay, and then the next one is the 1. So this is the component in the y direction, or the force in the y direction. Same thing, it causes counterclockwise rotation about C, so that's also negative. So it's just 1 over square root of 10 times 3, because it's 3 meters from here along the horizon. Right here, 2 and 1. Okay. And the next one is 800 Newton meters. Okay, this is a couple. So this one is applied. This is pure rotation, so this will be applied everywhere on this. So it's got to show up in every moment equation. So this causes counterclockwise rotation. So this is positive. And then we have the 400 newtons acting at 2 meters. And this is also positive because it causes counterclockwise rotation about C. Okay? So you can solve for FAB, and it's 843 newtons. Okay, so the next thing is to apply summation of the forces in the x direction, summation of the forces in the y direction. Both of them equal to 0. And if we do fx, what do we recognize here? That we're just going to have cx and the x component of this, okay? Which is 843 in this case, put a 43.3 times 3 over 100. So that's this side right here. Okay. So solving for that, what do we come up with? And it comes up to negative 800 newtons because we drew this off to the left, or the author drew this off to the left. Okay. So what it really means is Cx is actually 800 newtons going to the right. Okay. And it's good to indicate that some, indicate it. You can indicate it with an arrow. The author chose to do it this way. Either way, if you do it like this, then you don't necessarily need to go back to the free body diagram. So it's a good idea to add some notation. Otherwise, you'd have to go back and look, which direction is Cx in? Because Cx was drawn in this direction, and you notice that this is negative 800 newtons. What it really means is it's off to the right, okay? Well, in order to handle that, the author just chose to put 800 newtons and draw it off to the right, okay? All right, so the negative just tells us the wrong direction. And the Cy, you do the same thing for Cy. We have 400. We have the y component here, and we have Cy, the reaction here. And that makes up our equation. So minus Cy is going down, minus 400 is going down, and then this component is going up. And then you can solve for Cy. Okay. Okay, so here's another problem. And we're going to look for this wall crane supports a load of 700 pounds. And this is a frame and machine together. I'm going to use the same plan as before. We'll draw the free body diagram. Then we'll apply equations of equilibrium and solve for the unknowns. And if there's any, in this case, there's 2 force member here. But we also need to go up here and solve for D, right? So we're probably going to need to look at this in terms of multiple free body diagrams, right? Okay, so the first part here is to look at the pulley. This is the author's start. We're looking at the pulley. And really what we're looking at is like these tensions here, okay? Because how that is going to impact what's happening at the other supports. We need that, okay? So first part here is that we have 700 pounds going down. This is a cable. So we could do a free body diagram just of this pulley. And we have some tensions going up here, here, and a tension here in this cable, okay? And we can see the impact of that on these different supports. And of course, we can just solve for that. Of course, it's 2t minus 700. Tension in the cable is 350 pounds. Okay, then looking at the free body diagram for pulley C. And we have here the forces acting at C. We're going to have 350 going down, 350 going off to the left, okay? And then there's some reactions here, right? And this is at that point where it makes contact with the frame, right? The pulley wheel makes contact with the frame. So this is just simply going to be the 350 pounds in this direction, and also it's the same cable, so you have 350 pounds of tension going down here. So just solving these two equilibrium equations, Cx is 350 and Cy is also 350. Then we can look at free body diagram of pulley B. And one of the things you'll notice about this one is that since this cable is off on an angle, it's going to have both an X and a Y component, okay? So we need to consider that when we go through and solve this. All right, so just coming up with the equation. So here are the X components. You have minus BX, that's this one going off to the left, so it's negative. Plus 350, that's this. And then minus 350 times the sine of 30, which is essentially the X component of this tension, okay? And then you do the same thing with Y, okay? And from that perspective, doing Fy, you're going to have By minus 350, 30 degrees, right? So you just have this one and this component, the vertical component of this tension. Okay, so that gives us the reactions at B and C, and now we need to look at what's happening at B and A. And so we'll make a free body diagram of that, the support, this straight bar support, okay? So when we do that, we're going to have unknowns TBD, AX, and this is the tension here. And we don't know which direction it is, but we draw this off to the left. And what you'll notice is that you have some forces at this point, right, where it came together, where it met point B. So we have those forces, okay, the BX and the BY, which we found previously. And then what's happening over here from this perspective, from C's perspective. And looking at, what's happening at C, what you'll see if you took this and just kind of broke this out, what would you see? You'd see you'd have some force going off to the left in terms of the tension, which we previously found. Then you also have the 350 here, but you also have the 350 here, right? That's acting down from this point, from the actual connection point. So this end of the bar, what's actually happening, of 350 pulling this way and 350 here, so you have 700 pulling down, which should make sense because, you have a 700-pound force pulling down basically from the end of this bar. Okay, so one of the ways to do this is to solve for this force here. We know all these forces. The only ones, these are the three that we don't know. If I sum the moments about A, then TBD is the only unknown force. Okay, so here's TBD times the sine of 45. So it's a 45-degree angle. And it's times 4, so it's from here to here, which is 4 feet. And then this is the vertical component, okay? And it's positive because it would cause counterclockwise rotation about A, okay? And then the next one's the 303, and it's it's a negative because it causes clockwise rotation about A, and it's acting at 4 feet also. And this one has no impact on it because if you drew the line straight through, it doesn't cause a moment about A. And this one has no impact on it either, right? It's just this force 700 down, okay? And that's just going to be times 8 because it's 4 feet and 4 feet. And then you can solve for TBD, right? So TBD is 2409 pounds. Okay. Then what you can do is do the summation of the forces in the x direction. And when you do that, it's the same thing. The only thing that's unknown is going to be AX, right? Because now you know what TBD is. So you can find the x component of TBD. All right, and that's all this is. AX is positive because it's drawn off to the right. This is negative. This is due to TBD and the x component of that. And then 175 off to the right. And then minus 350, which is off to the left. So then you can solve for AX. Okay. Then we can solve for AY. And same thing. It's like AY up. This is the TBD component. Then it's minus 303.11 pounds going down. And minus 700s going down. So you can solve for AY. Okay. And then the next thing we want to do, we know all of the reactions at those points, or at those joints. Now what we want to do is we want to go and find it at FBD of member BD. Okay. Well, this is just a 2-force member, so we've already solved that problem. We know what this is, right? It's 2,409 pounds. And it's pulling down to the right, okay? So, and the reason is if you notice, this represents tension, okay? How did we know this is tension? Well, it's pulling, right? We drew it as being a pull from this point, okay? If we drew it straight into this point, it would be compression. Because the answer was positive, what that told us was that this is drawn in the correct direction. It's pulling from this point, right? So it's like trying to pull it back up. Well, what does that mean at this point? That means it's trying to pull down, right? So this cable is under not cable, but this bar is under tension, okay? So when we go to the next diagram, we're going to draw it straight down, pulling from this point, okay? Now you'll see that this problem just simplifies essentially into, um, you know, the x and the y components of TBD, right? What we already found before, okay? So it's just this is our x component. What that means essentially is that, you could actually say, dy plus this equals 0, right? Or you can write it this way, just saying, well, whatever this is equal to the negative of this. So you could say the summation of the forces in the x direction, it doesn't really matter. I mean, if you can recognize it right from this, it would say dx plus this thing equals 0. Okay, and then dy, this would be positive. Then it would be dy minus 2409 sine of 45 degrees equals 0. And then you just push this over to the other side of the equation. You come up with 1,700 pounds. Okay. All right. So what this really means is that, sorry, one too many here. What it really means is dx is not going off to the right. It's going off to the left, which makes sense. You're thinking, yeah, the reaction is going to be the opposite of whatever this is. Okay. And dy was drawn in the correct direction. Okay. So that's basically it.